Welcome to module 5 of chapter 8. In this module we are going to discuss various properties of automorphism group of a graph. If G is an automorphism, then we will associate a permutation matrix PG to it. We will show that a permutation G of an automorphism is an automorphism if and only if its permutation matrix commutes with adjacency matrix of the graph X. Automorphism group acts on the vertex set and as well as edge set. Automorphism will going to classify the graphs based on the action of its automorphism groups on subsets of vertex set. For example, a graph is said to be vertex transitive graph if it acts on the vertex set transitively, means that for any two vertices there exists an automorphism which takes one vertex to another vertex. In module 5 of chapter 8, we are going to discuss automorphism groups and its relation with adjacency matrix. Objectives of this module are relationship between automorphisms of a graph and its adjacency matrix, vertex and edge transitive graphs, distance transitive graphs. Recall two graphs x1 equal to v1 e1 and x2 equal to v2 e2 are said to be isomorphic. Written x1 is isomorphic to x2 if there is a one-to-one correspondence between v1 to v2, vertex set of x1 to vertex set of x2, that is there is a mapping psi v1 to v2 such that u1 v1 belongs to e1 if and only if psi of u1 comma psi of v1 belongs to e2. We discussed isomorphisms of graphs in module 5 of chapter 1 as well. So, now here we are going to discuss the results of all these in terms of adjacency matrix of a graph. The map psi is called isomorphism of x1 and x2, and isomorphism of x onto itself is called an automorphism. The collection of all automorphisms of a graph X denoted aut of x forms a group under composition of two maps. If X is a graph on n vertices, then automorphism of X is a subgroup of Sn, the symmetric group on n symbols. Under this correspondence, the maps in automorphism of X consist of n cross n permutation matrices. Also, for each G in automorphism of X corresponds a permutation matrix denoted by Pg. Now, we state two results, one of which gives a method to check whether a given permutation matrix is an element of automorphism of X or not, and other gives information about few eigenvalues of X. That means, when the graph is going to have few eigenvalues and how it affects automorphism group of X, or if the automorphism group have a nice structure, then the graph is going to have few eigenvalues. This is one of the important result. G belongs to automorphism of X if and only if its permutation matrix Pg commutes with adjacency matrix of the graph X. So, lemma statement is, let A be the adjacency matrix of a graph X, then G belongs to automorphism of X if and only if Pg into A equal to A into Pg. The proof, let G be a permutation of vertex set v1, v2 and so on vk, and G of vi is equal to vh and G of vj equal to vk. That means, G takes vertex vi to vertex vh and vertex vj to vertex vk. Each row of Pg has exactly one non-zero entry, namely 1. It is because Pg is a permutation matrix. So, it is a each row and each column has to contain only 1. So, now one has Pg into A ik, that is ikth entry of Pg into A is equal to summation T equal to 1 to n Pg IT into A Tk. So, which is equal to, since the ith row of or tth column of Pg contains exactly 1 1. So, we are going to have it becomes 1 only when in the H element, that means Pg IH is 1, remaining all other are 0. That is why this is equal to Pg IH into A HK. So, which is equal to A HK. Similarly, if you take A into Pg, its ikth entry, then it is equal to T is equal to 1 to n AIT into Pg Tk. So, in this case, in the tth row of Pg contains only 1 1, that is exactly when Pg of Jk as G maps Vj to Vk, that is why we have Pg Jkth entry is 1. So, we are going to get Aij. So, consequently, what we proved is AHK and Aij, they are equal if and only if Pga equal to Apg, if and only if Vh and Vk is an edge of E, if and only if V and Vj is an edge of E, that is if and only if G is an automorphism of X. Now, we are going to prove some applications of the previous result. The first one is, we are going to show that automorphism of X equal to automorphism of X complement. Corollary, let X be a graph, then automorphism of X equal to automorphism of X complement. First note that a matrix B commutes with J. Recall J is a matrix with every entry is 1. So, B commutes with J means JB equal to Bj. That means that actually if you multiply JB, what happens, the first entry is going to be the sum of entries in the first row. So, in that way JB equal to Bj means every row sum in B is equal to every column sum. So, consequently, every permutation matrix commutes with J. So, it is because the row sum or column sum of every permutation matrix is 1. So, every permutation matrix commutes with J. With this, now proof becomes easy. Pg into A equal to Apg, if and only if Pg into J minus I minus A. J minus I minus A is the adjacency matrix of X complement. So, which is equal to J minus I minus A into Pg. It is because Pg matrix, now Pg permutation matrix commutes with J as well as I always. So, we have this result. Now, we are going to show that automorphism group of complete graph or automorphism group of null graph is the symmetric group Sn. This proof is easy. The proof is obvious as every permutation matrix commutes with 0 matrix. 0 matrix is the adjacency matrix of the null graph, and further we know that Kn is equal to Nn complement. So, because of the previous theorem, automorphism group of Kn is equal to automorphism group of Nn complement, or it is equal to Nn. So, we have this part. Now, we are going to prove an important result. Let lambda comma A be an eigenpair of X. If lambda is a simple eigenvalue, then G belongs to automorphism of X, then Pg of Pg into A is equal to plus or minus A. That means, the eigenvector A of X is also behaves like an eigenvector of Pg. So, Pg is either plus A or minus A, that means that Pg A is also an eigenvector of Pg. As A into Pg of A is equal to Pg into AA, it is because G is an automorphism. So, Pg commutes with A. So, we have Pg into lambda A. We see that Pg A comma lambda is also an eigenpair. It is because we have capital A into Pg of A equal to Pg into lambda of A or lambda into Pg of A. So, Pg of A is also an eigenvector of A corresponding to eigenvalue lambda. So, Pg of A comma lambda is an eigenpair, but lambda is a simple eigenvalue of A. Hence, we have Pg of A is equal to mu into A for some mu belongs to R, a real number, as lambda is a real eigenvalue of X. It is because the adjacency matrix of a graph is a real symmetric matrix. The eigenvalues of real symmetric matrix are all real, that we proved earlier. So, Pg power S is equal to identity for some S belongs to N, as Pg is a permutation matrix. So, it is an element of the group Sn. So, there exists an S such that Pg power S equal to 1. So, we have u power S equal to 1, or since u is real, so u equal to plus or minus 1. If all eigenvalues of a graph X are simple, then its automorphism group is an elementary abelian group. So, there is a restriction on the automorphism group if all eigenvalues are simple. Okay. So, statement of the theorem is, if all eigenvalues of a graph X are simple, then automorphism group of X is an elementary abelian 2 group. If G is an automorphism of X, then using previous result, Pg of A equal to plus or minus A for all eigenvectors A of X, A of A. It is because every eigenvalue is a simple eigenvalue. So, some previous result we have this. As all eigenvectors of A forms a basis for R power n, so Pg of B equal to plus or minus B for all B belongs to R power n. Thus, Pg square equal to identity for all G belongs to automorphism of X. That means, for every automorphism G of X, we have G square equal to identity. So, that is why automorphism of X is an elementary abelian 2 group. Now, we are going to define a class of graphs called vertex transitive graphs. A graph X equal to V comma E is said to be vertex transitive graph if automorphism of X acts transitively on V. That is, for any two vertices x comma y in V, x not equal to y, there exists a automorphism G such that G of X equal to y. So, for every distinct vertices x and y, there is an automorphism which takes one to the other. So, because of this, what happens? All vertices will behave in the same way. So, automatically, consequently, vertex transitive graphs are regular graphs. Not only that, it has more property that we cannot distinguish one vertex to another vertex. We proved in the previous module, that is module 5 of chapter 1, that there exist regular graphs which are asymmetric. So, it is not only vertex transitive, it is not only regular, but it is more than that. For example, automorphism group of Kn is equal to Sn, automorphism group of cyclic graph Cn is dihedral group. Hence, the graphs Kn and Cn are vertex transitive. Johnson graphs and K cube graphs defined in the module 1 of chapter 6 are also vertex transitive. Let x equal to V comma E be a K regular vertex transitive graph. If lambda is a simple eigenvalue of x, then lambda equals k if mod V is odd and is contained in minus k comma k minus k plus 2 and so on k minus 2 comma k. So, for a K regular vertex transitive graph, already vertex transitive means it is regular, but we are assuming, we are specifying it is K regular. So, if lambda is an eigenvalue of lambda is a simple eigenvalue of A, then we are specifying what is its value is. It is going to be one of these only. So, but this is possible only if mod V is even. That means, if mod V is odd, then k equal to exactly equal to k. If mod V is even, then the lambda is one of these values minus k plus 2 and so on k minus 2 comma k. Now, we will prove an important result called a every Cayley graph is vertex transitive. Recall Cayley graphs we defined in chapter 6 of module 1. Let X equal to a Cayley graph on the group G with the connection set S. Then for every G belongs to G, X comma Y is an edge of X if and only if X Y inverse belongs to S. That is the definition of the Cayley graph. So, this is if and only if Gx into Gx means here Xg or Gx means that G acting on X, G of X, G take X to some other vertex. So, G of X or Xg into Yg or G of Y whole inverse which belongs to S. So, that means that G of X or Xg comma Yg is an edge of X. Hence, what we proved is G itself is a subset of automorphism of X. Hence, if A comma B belongs to vertex set V, that is in this case the Cayley graph vertex set is the group G, then the group element A inverse B takes A to B. We are not only proved it is vertex transitive, we showed which element is taking vertex A to vertex B. Now, recall a circulant graph, diagraph. A circulant diagraph means that its adjacency matrix is a circulant matrix. Let Zn denote the cyclic group of order n, then every Cayley diagraph Cay Zns is a circulant diagraph. Cayley graph Zns is a circulant graph. Conversely, every circulant diagraph Cayley Zns for some non-empty subset S of Zn. So, every Cayley diagraph is a actually every circulant diagraph is a Cayley graph. Hence, every circulant graph is vertex transitive. Every vertex transitive graph is not a Cayley graph, but every vertex transitive graph of prime order is circulant graph. Now, we will give an example of a vertex transitive graph, but not a Cayley graph. Peterson graph is that example. Show that Peterson graph is vertex transitive, but not a Cayley graph. The proof of vertex transitive is left an exercise. In fact, one can use the construction of Peterson graph given in these notes. It is known that up to isomorphism there are only two groups of order 10, namely cyclic group and dihedral group. It is easy to verify that none of the cubic Cayley graphs obtained from these groups is isomorphic to Peterson graph. We showed that every Cayley graph is vertex transitive graph, but converse is not true. Peterson graph is an example. Now, we are going to study few results on edge transitive graphs and distance transitive graphs. Now, we will discuss another class of graphs called edge transitive graphs. A graph X is said to be edge transitive if for any pair of edges there exists an automorphism which maps one edge to another. That is, if A comma B and C comma D are edges of graph X, then there exists an automorphism G belongs to aught of X such that G takes the edge AB to edge CD. The prism graph given below is a vertex transitive but not edge transitive graph. One can see that some of the edges cannot map to another edges. Complete bipartite graph KMN for M not equal to N are examples of edge transitive graphs that are not vertex transitive. If X is a be a connected graph, if X is edge transitive graph which is not vertex transitive, then X is bipartite. So, this theorem is characterizing which the graphs which are edge transitive but not vertex transitive, they are automatically bipartite graphs, there are only bipartite graphs. So, we let X comma Y be an edge of a graph X, W be any vertex of x, we define A is equal to T of x, that is where T is an automorphism, T of x is a vertex of x, and B is equal to T of y, again T is an automorphism here. As x is not vertex transitive, the sets A and B that corresponds to equivalence classes of the vertices x and y respectively, they are disjoint. Also, since x is edge transitive, so edge set of x is contained in A cross B, as the sets A and B gives a bipartition of V of x, as that is x is a bipartite graph. It is difficult to find an example of a regular connected graph which is edge transitive but not vertex transitive. One of the example is given below. So, but one has to check carefully. This graph is edge transitive but not vertex transitive, and further it is a regular graph. A graph x is said to be distance transitive if all the vertices u, v, x, y of x with distance of u comma v is equal to distance of x comma y, there is an automorphism satisfying g of u equal to x and g of v equal to y. That means a graph is a distance transitive graph if we take a pair of vertices such that their distance between them are equal. That means uv is one pair and xy is another pair, distance between them is equal, then automatically there exists an automorphism which takes u to x and v to y. So, that is why it is called a distance transitive graph. It is preserving the distances. The distance transitive graphs are clearly both vertex transitive and edge transitive. Complete graphs Kn, cycle graphs Cn, and complete bipartite graphs Kmn when m equal to n are few examples of distance transitive graphs. There are few class of graphs which attain the lower bound in the inequality d plus 1 is less than or equal to dimension of adjacency algebra of x less than or equal to n. The class of distance transitive graphs are one among them. That means, if x is a distance transitive graph, then the dimension of adjacency algebra of x is equal to exactly d plus 1. So, that is what the theorem states. If x is a distance transitive graph with a diameter d, then dimension of a of x equal to d plus 1. In fact, in case of distance transitive graph, something more is true, and to state it, we need the following definition. Let G be a group acting on a non-empty set V, then G also acts on V cross V by G of x y is equal to G of x comma G of y. For a fixed element u comma v of V cross V, the set, that is orbit of u v, is equal to set of all ordered pairs which takes u v by G. That means, G is varying here, u v is fixed. So, we are collecting all ordered pairs which are mapped by the automorphisms of G to u comma v. So, this is called orbit of u v under the action of G. The distinct orbits of u v under the action of G are called orbitals. So, in the context of a graph, that is x equal to v comma e, the orbitals of x are distinct orbits of the edge set v cross v under the action of automorphism of x. That is, orbitals are orbits of, arcs are non-arcs of the graph x. Arc means here just an edge, means here we are looking a direction as well. The number of orbitals is called rank of the graph x. Note that for each fixed u v belongs to v cross v, we can associate a 0 1 matrix Mij such that where Mij equal to 1 if Ij belongs to orbit of uv and 0 otherwise. The matrices obtained in by the above method are called orbital matrices. Also note that for any orbital matrix, all its non-zero entries either appear on the main diagonal or they appear on the off diagonal, as g of Vv is always equal to g of v comma g of v for all v belongs to v and g belongs to automorphism of x. The orbitals containing ones on the diagonal will be called diagonal orbits. If x is a distance transitive graph, then the orbital matrices and the distance matrices defined in module 2 of chapter 8 will coincide. Moreover, they form a basis for adjacency algebra of x. So, now we are going to prove an important result, that is decomposition of the complete graph on prime number of vertices as isomorphic copies of circulant diagrams. Let p be a prime number, let k be any factor of p minus 1, then the edge set of kp, that is zp comma e, the complete graph on p vertices can be partitioned into k subsets E1, E2 and so on Ek, such that the diagraphs xi equal to v comma ei for 1 less than or equal to I less than or equal to k are R regular circulant diagraphs where R is equal to p minus 1 by k. Moreover, the diagraphs xi and xj for 1 less than or equal to I less than j less than or equal to k are isomorphic. So, this contains two parts, we will prove one by one. Proof of the first part, let alpha be a generator of zp star, zp star means deleting 0 from p, zp, then h equal to alpha power k, 1 that is 1 alpha power k and so on alpha power k into r minus 1 is a subgroup of zp star having r elements, and let hj is equal to alpha power j into h for j equal to 0, 1, 2, 3 and so on k minus 1 be the cosets of h in zp star with h naught equal to h. It is important to note that hj as a subset of zp generates zp for each j equal to 0, 1, 2, 3 and so on k minus 1. Because of that, this is going to be useful, we will see how it is useful. Now, we will define a matrix Aj is equal to h belongs to capital Hj Wp power h. Recall Wp is the adjacency matrix of a directed cycle on p vertices. So, Wp is a circulant matrix and any polynomially circulant matrix. So, Aj is a circulant matrix, further it is a 0 1 matrix. So, Aj is a 0 1 circulant matrix. Let us now define a diagraph Hj by taking Zp as its vertex set, and for any x comma y belongs to Zp, x comma y is an edge of xj if and only if y minus x belongs to hj. Then it is easy to verify that xj is Cayley diagraph. So, that is Cayley of Zp comma hj. Since the cosets hj for 0 less than or equal to j less than or equal to k minus 1 are disjoint, one has obtained k disjoint diagraphs that are R regular, and this completes the proof of the first part. Now, we will prove the second part. We now need to show that all these k diagraphs xj for 0 less than or equal to j less than or equal to k minus 1 are mutually isomorphic. We will do so by proving that the diagraphs x0 and xj are isomorphic for 1 less than or equal to j less than or equal to k minus 1. Here we are changing j, but we are proving that xj is isomorphic to x0 where j is arbitrary. So, let us define the map psi from vertex set of x0 to vertex set of xj by psi of psi of s is equal to alpha power j into s for each s belongs to vertex set of x naught. Then it can be easily verified that psi is 1 1 and on 2. Thus, we just need to show that psi of x is an edge of x j if and only if x y is an edge of x 0, or equivalently we need to show that psi of x minus psi of y belongs to h j if and only if x minus y belongs to h, and this holds true as x minus y belongs to h if and only if alpha power j into x minus y belongs to h j, that is if and only if alpha power j into x minus alpha power j into y belongs to h j. This is same as psi of x minus psi of y belongs to h j. So, this completes the proof of the distance transitive graphs have lot of symmetry. Distance transitive graphs are vertex transitive as well as edge transitive graphs. The orbital matrices and distance matrices are coincide for distance transitive graphs. Further, they form a basis for adjacency algebra of these graphs. With this, we end this module as well as this chapter.